Actix Web is widely regarded as one of the most performant and memory-efficient web frameworks available today. Tech Empower's famous web framework benchmarks show it at the top of the pack, neck and neck with C and C++ web frameworks, and squarely above many of today's more popular backend web frameworks. You might think you need to concede to a poor developer experience in exchange for Actix Web's great performance. It actually turns out to be very developer-friendly, just as much so as today's other popular frameworks. Let's look at how to build a simple task management web service using Actix Web. Users can submit tasks to the service and query for their state. This pattern can be useful for many business applications where a user submits some asset or specification, maybe a 3D scene, waits for some process, like a 3D render, and expects some output file when the task is complete, like the rendered image of the 3D scene. We'll manage task state using an AWS DynamoDB table. So the first thing we're going to do is create the project. We're going to call it Actix Web Task Service. Now let's open that in our IDE. So the first thing we're going to do is set up our folder structure, and I'm not saying this is the optimal way to do this for a REST service, it's just the way I chose for this project. But we're going to have, inside the source folder, we're going to have, of course, Main.rs, and we're also going to have a model directory, and these will be Rust modules, an API directory, and a repository directory. So repository is where our kind of interfaces for our dependencies are going to go. Model is where the model for our APIs is going to go. And API is where the actual REST APIs are going to be defined. So let's go ahead and jump into our Cargo.toml file and add some dependencies that we're going to need. I'm not going to go into too much detail on these right now. We'll kind of talk about them as we use them. The first one we're going to need is Actix Web, of course. Go ahead and use whatever the current version is at the time you're watching this. And then we're going to use the UUID library to generate random UUIDs. We're going to use serde, of course, to serialize and deserialize our objects to and from JSON. And then we're going to use two crates for using AWS, one for getting the config and one for using DynamoDB. Then there's two crates for logging, which are useful if you're looking at the logs and you're trying to diagnose some issue. It'll show you the requests that are being received by Actix Web. Then there's two crates that are useful for dealing with enums. There's a crate called derive more that helps us automatically implement the toString method on our enums. And that should do it for our Cargo.toml. Now let's jump into Main.rs. So I mentioned all these folders that we created, the API, model, and repository directories are all going to be Rust modules. So the first thing we're going to do is declare the existence of the API module. So to do that, we'll do mod API. We'll implement that module later. Eventually, we're going to have a function in the API module called getTask. That'll be the API we use to query the state of a task. Again, we'll see red squigglies until we actually go and implement that. And then we're going to import some things from the Actix Web framework that I'll go over as we use them. Okay, next we're gonna use the Actix Web main macro on top of our main function to let the framework know that that's where it needs to start running. And our main function needs to be async, and it's got to return an IO result. Forgot a colon there. The red squiggly on that macro will go away as we implement the function. The first thing we're gonna do is set some logging variables that Actix Web reads to determine whether to do logging or not, and we want those on for the most part until we're in production, so we're gonna set those. Now we're going to create this HTTP server struct. That's kind of the meat and bones of an Actix Web application. So we're going to do HTTP server new. We're going to pass in a closure that sets up everything we need for our web application. And this closure is going to be run every time Actix Web spins up a new thread to handle requests. That's important to know for reasons I'll explain in a minute. Anything the closure references from before the closure, we want to move ownership to that closure. So that's what move does. To get logging to work, we have to pass in this default logger object. And then we're going to do app new, and we're going to call a function called wrap, and we're going to pass a logger in there. This will give us logging. Without this, you won't get anything on the console. So it's really hard to debug issues. And then we're going to do .service, and this is where you actually specify your handler functions. I'll get into more of what that means in a minute. But for now, assume we have one API, and it's called getTask. So assume that's implemented already. And then for our HTTP server object, we're going to bind to 127.0.0.1, port 80, run await. Okay, oops, this is actually a tuple in here that we passed to bind. A tuple consisting of the IP and the port, and then that could apparently cause an error, so we want to propagate that up the stack if an error happens. So now we're in good shape. So now we have, assuming we go and implement our getTask function, we should have a functioning web server. So the next thing we need to do is implement this API module that we created. First, we need to create a file called mod.rs. So we said mod API in our main.rs. The first thing the compiler is going to do is look for a file called api.rs. And if that's there, it'll use api.rs as that module. If that's not there, it'll look for a folder called API with a file inside that folder called mod.rs. And that mod.rs file defines all the files that are in that module. So we have a folder called API. Let's create the mod.rs file in there. And for now, we're just going to have one module within this module, and that's going to be mod task. So we're going to create a file called task in here. Task.rs. And this is going to define our task-related APIs. First, we're going to import a bunch of things from the Actix Web framework that we'll need later. And again, I'll go over those as we use them. Okay, that's about it for the imports. Now we're going to create our handler function, and we tie our handler function to a path that we want that handler function to receive requests for. And you also specify the HTTP method that you want this handler to handle. So in our case, we're going to handle gets to a path /task/ and you can put path parameters in here. So we're going to have a path parameter called task global ID. So you enclose path parameters in curly braces, and then our handler function has to be async. So, and we're going to make it public, so it can be called from or referenced from main.rs. And we're going to call it getTask. It's not going to take any parameters. We'll add some in a minute. Handler functions have to return one of two things: either a struct that implements the responder trait, or a result for which the success value implements the responder trait and the error value implements response error. For now, we're just going to use a struct that implements response. Actix Web provides a handy one that a lot of people will probably use called JSON. We're going to say JSON, and right now it's just going to be a string. The framework already has built-in implementations of responder for JSON string, so that's kind of handy. We're just going to return JSON hello world. Okay, and that should be all we need to make a simple Hello World API. Obviously, we're going to expand on this implementation. I just wanted to show you kind of what the starting point is. We're going to start adding a few more things. First, we want to do something with this task global ID path parameter. Let's look at how to extract that from within the handler function. First, we need to make a struct to kind of take in that path parameter. Pub struct task identifier. And of course, we need that to implement serialize and deserialize. And it's going to only have one field, and that field name has to match the name of the path parameter that you specify in the get macro. So that's going to be task global ID. Now that we have that, we need to explain something called extractors. Extractors in the Actix Web framework are a means of getting at various parts of the request from within your handler function. And the way we use extractors is we actually add parameters to our handler function. And if those parameters implement the from request trait, that's considered an extractor. And the Actix Web framework will actually automatically populate those parameters with the appropriate values. Let me show you what I mean. So in the case of path parameters, there's a type built into the Actix Web framework called path. So we're going to add a parameter to getTask, and we're going to call it task identifier. And it's of type path of task identifier, the struct that we made. Just by doing that, just by seeing that we have a parameter of type path, the Actix Web framework is going to automatically inject or try to deserialize the path parameters into the struct that we specify, in our case, task identifier. So those values are then going to be made available to our handler function. If we had multiple path parameters, we just have multiple fields in our struct that we use. And so now we can actually do hello world, and instead of the hard-coded string, we can do task identifier to inner, and then get at the task ID. And so this should actually return in the response the task ID. And now, so we've seen how to use the path extractor. There's also an extractor for query parameters called query that we're not going to use in this example. If you want to get at the body of the request, you can actually use that JSON type again, the same one we use to return a value from the function. So you can do body JSON. So JSON not only implements responder, it also implements from request. So it's also an extractor. So you can do JSON of whatever struct represents your request. It'll automatically deserialize the contents of the body into the struct that you specify. So that's kind of cool. Now that we've covered how to make a simple API, it's time to read and write from a database. So to do that, we'll actually add to our repository module, we'll add a file called Main.rs, and that's going to refer to another module called DDB that we'll create. This is going to have a struct that contains our interface with DynamoDB. I'm going to implement that. The implementation is a little bit hairy. I'm not going to go over too much of it. I'll link the full code for this project down below, so if you want to dig into it, you can. In a previous video called Rust on AWS, I went into the details of how to use DynamoDB from Rust. So I'll link that video here if you're interested in watching that. You don't necessarily need to watch that to understand this video. The important things to know here are that we have a struct called DDB repository. That's going to be the interface between our APIs and DynamoDB. It has three important methods. It has init, which we use to create it, and it has a put task and get task. And so those are the functions our APIs will use. So put task takes a task. Under the hood, it writes it to DynamoDB. And get task takes a task ID and returns a task if that task exists. Those are the important things to know there. And so in under the hood, we translate fields in our task to DynamoDB fields and vice versa. Okay, so now that we have our DynamoDB implementation, we need to import that in main. Ultimately, we need to access that DynamoDB struct from our handler functions. It's tricky because our handler functions are not actually invoked by us, they're invoked by the framework. So we need some way of kind of injecting that DynamoDB object into our handler functions. And the way we do that is with a concept called shared data in the Actix Web framework. When we create our app, we can use a function just like we called this service function to refer to our handler function. There's another function called app data that allows us to pass in some kind of shared state that will be injected by the framework into our handler functions. First, though, we need to create our DynamoDB repository object. Let's import that. We need to declare that we have a module called repository. Oh, private. We need to make this public. We need to make this public too. Okay, now we need to instantiate the AWS config, which we pass into the DDB repository init function. Oops, AWS config. The tricky thing about this is that because this closure in here where we're constructing the app is actually not async, we can't instantiate the AWS config from within that non-async function. So we have to do it before. First, let's try to instantiate the DDB repository out here before the closure, and it won't work, as you'll see. And this init function takes two arguments. First, the table name, and then the configuration that we just created. Oops. To pass shared data in, to get it injected to all your handler functions, you need to use the data object, which I believe implements the from request trait, and then you kind of wrap your whatever shared data you have inside that data object. So we'll call it DDB data, and just pass in DDB repo. And then let's try passing in DDB data here. The interesting thing is if we define our DDB data object out here and use it, pass it into app data, because we're creating a new app object for every thread that Actix Web creates, it'll actually fail because DDB repository doesn't implement the share and send traits, which are automatically added by the compiler if it deems some struct to be thread safe. So what we actually need to do is create all this stuff inside the closure like that. The config can still be outside the closure because we clone it here. So we create a copy for every thread. Now each thread has its own DDB repository object. I'm not sure if the AWS client is actually not thread safe. I think in other languages can be used across threads without a problem, the same client object, but I just thought that was interesting. But yeah, in this case, as of now, the AWS SDK is pre-release, so this could change, but right now it is not deemed by the Rust compiler to be thread safe. So we need to create one per thread. Now we're gonna dive more into the model that we're gonna use for our APIs. So inside this model module, we're gonna create another Main.rs, and we're gonna create a module inside that called task. So create a file called task. All right, so we're gonna definitely need serde for this because our model will need to be serialized and deserialized. The strum macros help us with converting a string to an enum value and vice versa. Let's first create the task struct. It's going to need to be serialized, so we're going to derive serialize. It's going to have 6 fields, the first of which is the UUID of the user that created it. In this video, we're not going to talk about the user APIs, but we're going to assume there's some set of users and each one can create one or more tasks. And each task needs to be associated back with that user in case we want to list all the tasks for a given user, for example. And then there's going to be a task UUID as well. We're going to assume there's like a task type. There might be a 3D rendering task, and there might be if you're running a telescope service, a task might be to take a picture of a certain place in the sky. And then we're gonna have a state, which is what state that task is in. We'll implement the task state enum next. And then we're gonna assume for every task, there's a source file, which is what our task will read from, and then also a result file, which is what, when the task is done, the user will be given the results in some file. There's always a source file, so that's a string, and there's, source file. And there's only going to be a result file sometimes, and only when the task is actually completed. So that's going to be an option. Okay, so that's the bread and butter of the task model. Now we're going to have a task state, not started, in progress, completed, paused, failed. And we're going to have APIs to put it in each of these states. And we're going to have a few simple helper methods for task. First, for creating a new task. When we're creating a new task, we don't need to specify all the parameters. There's some that are implied. When we first create a task, it'll always be in a not started state to begin with, and we need to create a random UID and things like that. So this is kind of a convenience function. We're going to make use of this shorthand where you specify a variable name, and if it matches the field name of the struct that you're constructing, you can just pass in the variable and it'll infer that it goes to the field of the same name. We're going to create a random UID for task UID. It's always going to be in a not started state when we first create it. And there's never going to be a result file when we first create the task. So we just pass in none for that option. Next, we're going to create a function called, so we have this concept of global ID, which is going to be the user ID concatenated with the task UID. The reason for that is related to our DynamoDB schema. This video is not about DynamoDB schema, but yeah, that's the reason why. It's going to return a string. That's going to be format. We're going to have another function called canTransitionTo, and that's going to tell the consumer whether a given task can be transitioned to a given state. And in the real world, this would be a little more complicated, but for our purposes, we're just going to say yes if the consumer is trying to transition the task into a state other than the one it's currently in. Task state, and it's going to return a bool. We're just going to return self.state is not equal to the state we passed in. That's it for our task model. Now that we finished the task model, we're going to go back to the API task.rs and continue with this implementation. So we know about extractors, we know about responders. So now that we built the task model, let's go back to the task API and build out more of those structs that we'll need for the requests and responses to our APIs. So we have task identifier to grab the task ID from path param, and we'll use that in some of the other APIs as well. The other thing we'll need is task completion request. And this is for the case where we want to complete a task and we want to assign a result file to that task. So we'll create a struct that just has one field, and that's a string that points to the result file. And again, this comes from the request body, so we'll need to deserialize that. Okay. There we go. So this will only be used in the complete task API. The other thing we need is a submit task request. So when a user submits a task, we'll need their user ID to be supplied and also the type of the task and the source file that that task will be referred to. So there's 3 fields there. This will also come from our request body. The next thing we'll need is an enum for the errors that could possibly happen in any of these APIs. And I'll explain how error handling works in a minute. But for now, all we need to know is that we have an enum that potentially we return if an error happens. And the enum value refers to what went wrong. And each enum value ultimately is going to be mapped to a specific HTTP error code. So let's do pub enum task error. And then one possibility is task wasn't found. We tried to update a task, but it failed. So task not found obviously will be a 404. Update failure, there's a few options there. And then task creation failure. And then bad task request, this will be a 400. I mentioned earlier that we can return a struct that implements responder, or we can return a result for which the success value is a responder and the error value is an implementation of response error. And so our task error is what we're going to use to implement response error. And so we're going to create an implementation of response error for this task error enum. Again, response error is a trait implemented by the Actix Web framework, just like responder or from request. There's two functions here. One is we're going to tell it how to respond. This function will actually return a responder. And the most kind of fine-grained way to control your API response is by using an HTTP response object, which implements responder. And that gives you fine-grained control over what the body of the request is, what the response code is, things like that. In our APIs, we don't use that because we don't need that fine-grained control. We just return a JSON object and we let the Actix Web framework convert that JSON object to a response. But for errors, we implement error response. In our case, we're just going to create a response object. It's going to be JSON, and the body is actually going to be and you wouldn't do this in production, but the body is going to be the string that represents the enum value. So if we get a task not found error, we're literally going to return to the client task not found, the string, which actually technically isn't JSON. This content type might not be the best choice, but typically here you'd return JSON, but you could easily convert this enum value into JSON if you like. Oh, and for task error, we also need to implement debug and display. Those are used by the response error function. Oops, typo. Okay, now we're in good shape there. The other function we need to implement from response error is the status code. That's what tells the framework what status code to return with the response. And so we're just going to map each enum value to a HTTP status code. So we're just going to do a match statement here and go through each enum value and map that directly to a status code. Okay, so now our task error struct is ready for use in our APIs. So now instead of returning, we're going to get rid of this body here because for get task, we don't look at the request body. And instead of returning just JSON, we're going to return result. And then it's going to be JSON of a task. We need to pull in the task model. So to make that model module available to other modules, we have to make sure we declare it in Main.rs as a module. Then it becomes available to the API module. So we're going to grab the task struct and task state. And so now we should be able to return a result for which the success value is a JSON representation of a task and the error result, or the error value, is a task error. So now we're actually going to make a database request. So calling the getTask function of the DDB repository struct that we created, we're going to use the task identifier that we got from the path param. Into inner extracts that value from the path object. And then we have our task identifier struct, and we grab the task global ID value from that. And that's asynchronous. So we do await. We use a match statement here to find out if there was an error or we got a success value. If there was an error, we convert that from whatever error the DDB repository threw, which returned, which is DDB error, I think. And then we convert that to a task error. Yeah, the getTask function of the DDB repository returns an option of a task. So we actually just check if it's some or none. And if it's none, then we return an error, a task error, task not found. And then if it's some, then we return OK, and then the JSON value of a task. We also need to use the extractor for shared data. So that's data DDB. Let me break these out so it's easier to read. The repo data of a DDB repository. Do we import that? Oh, we need to import the repository object. So we're importing the DDB repository struct from the repository module. Okay, that's it for our get API. Now we just need to make APIs to submit a task, fail a task, pause a task, start a task, and complete a task. And all those, as you can imagine, are going to share pretty similar logic. They're all going to call put task on the DDB repository, just with slightly different values. So we're going to make a helper function to facilitate that. It's going to be called state transition. It's going to return a result where the success value is the JSON representation of a task ID, which is not really necessary for these APIs, but I wanted to return something to show in the example. So we're just going to return the ID, kind of echo back the ID of the task that was modified if it was successful. The consumers of the state transition function will just kind of hot potato the result of this function back to the framework. The first thing we need to do is get the task that we're trying to change the state for. So, and if we find the task, we assign the task to this task variable right here. If not, we need to return a task not found error. Okay, so now that we got the task, we need to change the state to the new state. Well, first we need to see if that state transition is allowed. If a task is in progress state and we try to start it again, we should return an error in that case. So that'll be a bad task request. So we're gonna do if we can't transition to the new state, return a bad task request. And then if we got this far, so set the state of the task to the new state that we got from the consuming function. And then if result file is not none, set the result file. Now we need to offload the task identifier to a local variable, because the task variable is going to hand it off to a different function. So we won't have access to that anymore after it's handed off, after the ownership changes. Now we're going to call put task. And if that succeeds, we return the task identifier that I mentioned. So we echo back the task identifier with the 200 response. If there's an error, we just return update failure. What's going on here? Fix that. Okay, that should do it for that function. Now we can start implementing all the other APIs that leverage that function. So I'm just going to kind of go over one of these APIs and then breeze through the rest because they're all pretty similar. There's no real new concepts here. So instead of a get, this is a put. And this one's going to be start task. And then after the path param, the ID path param, we're going to just have the string start. It takes a repository and a task identifier just like the get flavor does, and returns a task ID or an error just also like the get flavor does. And then we call that state transition function that we created, pass the repo. Our desired state is in progress and our result file is none, and we're going to call await on that. Oops. Yeah, so that's it for our start task. The other state transition functions are going to be the same. The major difference is that the complete task is going to have a result file. That's pretty much it. Okay, yeah, and you can see that result file here. Task state. We need to implement serialize. Okay, so that's here. Aha. Yeah, we need to implement all those to facilitate the responder. The get task function needs serialize. Sorry, get task needs enum string because we're converting a string value in the database to an enum value in our code. Display is needed to convert to string, and then equality is required. So for when we check to see what state the task is in before we transition it to a new state, to see if that transition is allowed, we need to check enum equality. So those are what those are for. The last thing we'll need to do is implement the submit task API to allow users to create tasks. And that's going to be a post. So we're going to leverage the task new function that we created earlier to make creating the task simpler. Again, that new function takes 3 parameters, the user ID who's creating the task, the task type, and the source file. So once we've created that task, we're going to get the global ID of that task before we write it to the database, because that task variable is going to change ownership when we pass it to the put task function. So let's grab that identifier. And then we're going to call put task and call match on the value it returns. If it's successful, we're going to return the ID of the newly created task. If it failed, we're going to return a task creation failure task error. typo. Submit task request has a task type field that I made a typo on. Now that we've created all these other APIs, we need to go back to Main.rs and add a service call for each one of those APIs. So submit task. We need to make sure we import all the functions that we created so we can add them to our app. Submit start, that should do it. Okay, we've added all of our functions to our app. Let's indent that. Now let's build and run this and see if it works. Okay, we're gonna use Postman to try to create a task. So we're doing a post to localhost/task. Let's see if that works. Looks like we got a 200 response. We got a task ID back. So we can copy and paste that task ID into the other API or request for the other APIs. So let's call get task and see if that returns the correct result. Okay, we got a task. We can see it's got a task ID. All the fields look like they've been populated correctly. Now let's try to start it. Okay, we got a task ID back, which means it was successful. Now let's get the task again. So we should see the state transition from not started to started or in progress. And looks like that's the case. Now let's try complete task. Complete task will include a request body with the result. Instead of a null result file, we should see a path there after we complete the task. And then the state should be in a completed state. Okay, that was successful. Let's try this again. Okay, so we got result.png is now the result file, and the task is in a completed state. So that's a simple REST service using Actix Web. I was actually really pleasantly surprised with the developer experience of the framework. The framework is widely known to be very, very fast. Like I said, it's neck and neck with some of the C and C++ web frameworks. I was kind of expecting to have to make some concessions on the developer experience in order to get that extra performance, but I didn't get the sense that I was making any concessions. I feel like the framework is just as simple as something like Spring Boot or Express.js or any of the other popular frameworks I've used. So that was a pleasant surprise. The biggest hurdle you might have in learning Actix Web is using the Rust programming language, which is not that bad. I personally don't see a good reason not to use Actix Web, even for web apps that are not performance critical, just because there's almost no extra investment aside from learning Rust. I plan to use it for all my web apps going forward, unless there is some dependency of the web service that requires using a Java client or a client that's written in some other language for which there's no Rust equivalent. I could see that being as the only reason that I would not use it. Or if there's some desire for language homogeny. So if we're using TypeScript on the front end, there might be a desire to use TypeScript on the back end as well. So it's easier to copy code to and from the front end and the back end. I'd see that as a fair reason for not using Actix Web. Other than that, yeah, again, I plan to use it for all my REST services going forward. The performance difference between it and other web frameworks is pretty large. There's no one benchmark that kind of tells the whole story there, but if you look into the various benchmarks that have been done, comparing Actix Web to other frameworks on the market, you'll quickly realize that there's a pretty big difference in most cases. Hope you guys liked it, and we'll see you in the next one.